morning, everybody. Or I always do that. Yeah, or afternoon or evening. I see Ben's smiling face down there, and I realize it's not morning everywhere. I'm John Mallinckrodt. I'm your host for the Bite of Physics, and we are now venturing into the hundreds. We're at Bite of Physics number 102, although I am recycling a bit from Bite of Physics number 30. And I have a kind of a stripped down version of Bite of Physics number 30 for you, where I'm going to try to present quantum entanglement without actually saying anything about quantum entanglement. And I know there's at least one person on the stage who will have a few things to say along the way. Maybe, and I expect a hearty conversation afterwards. But we'll see how this goes. We'll get an indication of just how tired everybody is of quantum entanglement. I think it's fascinating, and I know that Benjamin thinks it's fascinating too, as well as wrong. So we'll get into all of that, but I do want to just kind of do a stripped down version of number 30 today, and I think it's kind of better that way. I think it's got more punch. We'll see how it goes. But before I do, I'll just say hi to everybody on stage. Shamash, a.k.a. Logic Guy, I think is probably streaming by now onto YouTube as well.
Yes,
and you'll
sir. This is the first time after 102 bites that I get exactly your intro, not more, not less.
All
so
right.
I'm very proud of myself that I could do that.
You're getting good at this.
Yeah, and that's all thanks to you. That's all thanks to the great practice that you're providing, and I hope that you keep providing it.
Well, thanks, Shamash. And if you'll put that YouTube link in there, maybe some people will want to watch it
right
on
away.
YouTube. Yeah, great. Thank you. And we'll say hi to Ben Tristram, my very valued sidekick and substitute when I'm away. How you doing, Ben?
Hey, man. Good. Thank you. Yeah, glad to be here, as always. Busy short-circuiting 12-volt batteries with large reels of cables to load test them. I'm like, how fucking long does this cable reel need to be for this not to blow up? But I found a several 100-meter reel with 3 ohm resistance, and nothing blew up when I plugged it in. So, yeah.
Hell, that's great.
Just little sparks.
Ben and Benjamin both share an ability to actually make stuff and make stuff work, which I can't do. I can just kind of talk about theoretical nonsense. So yeah, it's always good. I wish Ben were closer because I've got some work around the house for him, but I suspect he probably has his hands filled with his off the grid or semi off the grid projects all the time. And Benjamin, last but certainly not least this time of all times, welcome to the stage. I was, of course, hoping you would be here.
Hey, I'm excited. Yeah, you and I discussed this just 2 days ago.
Yesterday.
And I have a very fresh off the pages new experiment that replaces Bell's theorem with a different way of getting at the difference between Einstein and Bohr. It doesn't require entanglement. I'm very excited. And we can talk about it later, of course.
Yeah, definitely later, because I do want to kind of present this without really saying any of those words you just said, even though I kind of say quantum entanglement. And then, but we will definitely get to all of that stuff in the aftermath. Ben, I saw you unmute. Did you want to say something?
No, it's all Paul.
Okay. All right, well, let's just get right into it. This is, as I say, kind of a redo of Bite of Physics number 30. You can always look that up there at the links on the first page. There's a link to all the Bites of Physics, and you can find number 30 along with all the others and a bunch of other things as well there, if you care to. So getting right into it, on slide 2, as I already said, in Bite of Physics number 30, I did a kind of a more complete version of this, but the focus was on probably one of my all-time favorite papers in physics by David Merman, published in a journal that I edited for a year one time, and is, I think, the best journal in physics. I know that it's the most read journal in physics by physicists. It's called the American Journal of Physics, and it focuses on papers written for physicists usually, but out of their expertise, pedagogically oriented papers on topics that a physicist might not know much about because it's not in his particular or her area of expertise. So David Mermin wrote this paper on the topic of quantum entanglement. He's written three such papers, each one of which he calls kind of a simplification of this one. But I still believe that this is the best, I think the most easily accessible paper that he's written on the topic. And it's down there at the bottom. It's completely accessible to rational fraction calculation. Oh, capable people, I should have said there at the bottom. So if you care to download it and take a look at it later, there it is. It's only 4 pages, I think, really like 3 pages, maybe 2 pages of meat. Has nothing beyond elementary kind of probability ideas and fractions and that kind of stuff. And it talks about a topic that is it talks about an idealized version of an experiment that can be done, that has been done many times, and that has recently earned 3 people the Nobel Prize in Physics, and that's now done routinely, as I always say to Benjamin's chagrin, by pimply-faced teenagers in upper division undergraduate physics labs. And don't worry, Benjamin, we'll get into your objections. Benjamin has certain objections, which I can't fully answer to all of this. But we'll see how it goes, and we'll talk. We'll talk as long as Benjamin wants, and as long as I don't get too hungry for lunch or breakfast in the aftermath. So here's the experiment on page 3. Experiment's pretty simple. This is an idea. Go ahead, Benjamin.
Can I just add that you're far from the only one who can't answer these questions? That these questions are sort of universally unanswered.
Yeah, I'm not sure I buy that, but we'll get into all that. Fair enough. I'll just take that as a possibility right now. So on slide 3, you see the experiment. Experiment is there's a box in the middle that shoots 2 particles out, and these 2 particles then venture on to 2 detectors, each one of which has 2 lights and a 3-way switch. Entangled particles emerge. I say entangled particles. I shouldn't even say that. For the purposes of this, I'm just going to say a couple particles emerge from box C, and they head on toward these 2 detectors. And when they get to those detectors, each one of which has a three setting switch set to some number. One is set to 1, one's set to the other, whatever. When each particle reaches its detector, one of its lights, red or green, flashes. That's the experiment. It's pretty simple. And you do this setting the switches randomly, however you want. Set them any way you want. 2, 1, 2, and 3. Each one gets set independently, however you like. Hopefully you do it representatively. You do it randomly enough that you kind of cover all the possibilities. The best thing is to set them randomly so that you make sure that each one is set to switch 1 an equal number of times, set 2, switch 2 a third of the time, switch 3 a third of the time, etc. So each one does that. Every time, all the times that detector 1 is set to 1, detector B is set 1/3 of the time to 1, 1/3 of the time to 2, 1/3 of the time to 3. That's the best way to do it, but it doesn't matter how you do it. You can set these switches any way you want, and you'll still get the same conundrum ultimately. Maybe I shouldn't say that. It is kind of important that you cover all the bases. So let's assume, for the sake of argument, that you do randomly set all these switches so that you get all the possibilities over time, when you've taken millions and millions of data points, let's say, that you've really statistically covered all the bases.
Just to make sure that we understood, there's 2 machines. They are identical, A and B. They have 3 settings each. setting 1, setting 2, setting 3, and you have two particles of the same type going from C. And
Just two particles. I wouldn't qualify it by saying of the same type. There's just two particles that emerge
just any
from
two
C.
particles. All right, cool. And the detector's job, so A and B's job, is to say whether 3 applies to the particle or not. So if it does, it goes green. If it doesn't, it goes red, right?
No, not that.
No.
It's just that when the particle hits the detector, one of the two lights flashes. We don't know which. The switch setting doesn't tell us immediately, and we don't know anything about the particle, so we can't tell. But the particle, if the switch is set to 3, the light may flash red. The light may flash green. A light flashes.
You do realize that for someone who is very uninitiated with this looks very strange and random, right?
Well, I mean, I don't think it should yet look that way. Maybe the switches don't do anything, right? A particle comes in, and because of some property of the particle, the red light flashes or the green light flashes. Maybe the switches don't do anything. They don't have to. There's just switches on the front, and when a particle enters, one of the lights flashes.
All right, cool.
Okay, and then we don't have to hypothesize anything else than that. You can set the switch to any position, and when the particle enters, one of the lights flashes. That's all you need to know. Okay, yeah, that's probably good to know. I mean, it's not like we're determining in any obvious way which light flashes with the switch setting, but we'll see some things.
I'm asking about the meaning. So does red mean success or failure, or is just
Nope.
We don't know what it does? Just does that?
Doesn't
Just a
matter,
red
it's
light.
how that particle interacts with that box just
Yeah.
causes red light to flash for whatever reason.
Okay.
Yeah, they're just two lights, and they're colored red and green so that we can call them red and green. But that's all that you need to know. When a particle gets to the box, one of the lights flashes, and we can describe it as red or green. So when you do this run over and over and over again, you collect data of the form shown on slide 4. Each run produces a result.
We got to ask about the source of that data, John. That's just this data. We got to know where the data came. Is this the authentic data that you have?
This is all an idealized. It's really important to understand. This is an idealized version. I won't even tell you. I won't even tell you necessarily. I'm just describing a thing. It does turn out that you can make an experiment that does do what I'm saying in a slightly different form. The statistics that I'll be describing are exactly statistics of a real experiment that could be done. Whether it has been done, I'm not entirely sure. But Merman describes the experiment in detail for those who have sufficient physics understanding to appreciate it in an appendix. But you don't need to read that appendix to understand the implications of the data. So this is an idealized version. It's idealized because there are no you get, basically you're to assume that the lights only flash when one of these particles, when one of a pair of particles enters. That's not true in a real experiment. You have to assume that every time a detector enters, a light flashes. That's not true in a real experiment. There's all sorts of things that will mean that you'll have to do some statistical analysis on the results, and that's one of the things Benjamin will have some comments to make on at the end.
You bet.
Sorry?
Nothing, carry on.
Okay. So every time we do this, every time a pair of particles goes out, we collect data like this. 23GR means the first detector was set to switch setting 2, the second one was set to switch setting 3, and the first detector flashed a green light, and the second detector flashed a red light. So that's what 23GR means. Every time you get a data point from this device, you get that. That's the data. 23GR is the data from one run of this experiment. Make sense? I mean, just you understand that. And so there's a whole bunch of possible results shown. That's as Merman says, it's a fragment of a page of a volume from the set of notebooks recording a very long series of runs in this idealized, not actual, but idealized version of an experiment that can be done in the way that he talks. Okay, so any other comments or questions? Oh, by the way, sorry, do come up on stage if you like. I always encourage people to come up on stage, but of course you're welcome to just hang out down there. If you make comments in the chat, I'll try to see them from time to time, but I'll only be able to read them, Amir, if they're in English. Sorry. maybe Shamash or somebody else can translate for me.
The only one who can say, I think this is Persian. This is out of my territory right
We
here.
need Sam, yeah. Okay. Anyway, feel free to come up on stage if you like. Go ahead.
When you say this is like a tiny segment of all the real data, the Delph data set only published 250 events.
Right.
This data seems to be 8 times about, I don't know, 16, 64.
Well, Merman here is obviously just making a point that he wants to be clear that we want to run this experiment and get an infinite number of points. That's what he'd like to do. If it's an idealized experiment, why not? Let's just take infinite data points.
Is 250 in your book.
Oh, well, remember, this is a fragment of a page of a volume from a set of notebooks.
Just conceptually, how close to ideal is the number 250?
Yeah, well, of course, in a real experiment, that's going to depend on things like how uncertain results are, the variability of results. You would want to do an experiment like this, take many runs and see what the variability in the results are. It's better to take 1,000 runs and then consider them to be 10 100 run experiments than it is to simply do 1,000 runs.
Especially if you can throw some out, right?
Especially if you can throw some out. Yeah, and we'll get into all of that too. Those of you who know Benjamin know what he's referring to there. Okay, so those are what the runs look like. Here's what the data analysis looks like. Here's what the data looks like when you analyze all of those runs. What you find is that let's see, did I say this? Oh, yeah, sorry. So what you find is that when the two detectors had the same switch setting, that's what we're going to call case A, set to the same numbers, detector A set to 3, detector B set to 3, or 2 and 2, or 1 and 1. Whenever the switches are the same, then the lights that flash are always the same color. Right, with no errors. That's a part of this idealized version. In a real experiment, sometimes they would flash differently, but in this idealized experiment that we're talking about, whenever the same numbers are on the two detectors, you get the same color lights, both red or both green. That's always what happens. You never get a red and a green or a green and a red. Okay, so that should be pretty simple to understand. If the switches are set to the same numbers, you get the same color. If the switches are set to different numbers, which is the only other possibility, then you get the same color 1/4 of the time, and you get different colors 3/4 of the time. That's just what you get in the data. In this idealized experiment that can't be done because no experiment is idealized.
Can we assume that they are also evenly distributed? So half the times you get red, half the times you get green?
Yes, thank you very much. I should have said that. It is important to understand there's no biases in this data. in those times when you get the same color, half the time you get red, red, half the time you get green, green, et cetera. And half the time you get RG, half the time you get GR when those are. So there's no biases. This data, this table completely covers the results as long as you add the fact that there's no red-green bias or 1, 2, or 3 bias in the data whatsoever. Okay. All right. So let's move on to slide 6. How can we explain case A? Remember, case A is when the detectors are set to the same number. How do you explain that? Well, it's pretty easy. The concept of instruction sets is probably the way to go. And that is to say that there's some real property, and that is an important word we'll get into later as well. It's a real property of the particle itself in conjunction with the switch setting determines which light will flash. And so that effectively, like the property could be a little knob on one side, or maybe the particle's bumpy in a certain way. Maybe the particles have different masses. Maybe they travel at different speeds in the ranges. It doesn't really matter, but there's some real property that the particles have that effectively means each particle carries one of 8 possible instruction sets shown there. RRR, GGG, etc. And let me explain what I mean by that. An instruction set like RRR would mean if it's switch 1, flash red. If the switch is set to 2, flash red. If the switch is set to 3, flash red. An instruction set like RGG will cause its detector to flash red if its switch is set to position 1, and green if the detector is set to position 2 or 3. So the instruction sets simply tell the detector which light to flash depending on where it switches. And you just need that kind of thing. There's only 8 possible instruction sets. I think you can verify for yourself. Go ahead, Shamash.
This instruction set could stand for a physical property in the particle, right?
Right. And that's what we would expect, is that it reflects a real physical property of the particle. We're just encoding it in this way. Okay, so you can think about that. Notice I have grouped the 8 possible instruction sets into the 2 that are always red or always green. In other words, those type 1 instruction sets will make the light flash either red or green independent of what the switch is. It doesn't matter what the switch is set to. An RR particle will always make the light flash red, and a GGG particle will always make the detector flash green. Whereas the other instruction sets are a little more subtle. Sometimes, regardless of what switch setting, sometimes it'll flash red, sometimes it'll flash green. Okay, so I've called those type 1 and type 2 instruction sets. And it's important to distinguish. This is the part that's kind of easy to get confused about in your head. I've talked about case A and case B. Case A is when both switches are set to the same number. Case B is when they're not. Type 1 instruction sets are instruction sets that will make one color flash regardless of the switch setting. And type 2 instruction sets are sets that it will depend on the switch setting, which light flashes. Okay, any comments, questions on any of that? Welcome, Steve and Bert and Sam. Let me just take a quick pause and just see if any of you guys are itching to ask a question or make a comment.
I came in late, so I'm going to save it because you may have covered it before I got here.
Okay, that's fine. Good to see you, Steve. Thanks
Great
for coming.
To see you.
Hey, Bert.
Hello, everyone. And I'm just catching up. I just joined a few minutes ago.
Okay. And good morning, Sam. Thanks for being here and doing the heavy lifting. Oh, wait a minute. Let me see.
Good morning, everyone. Sorry I'm late.
No problem. Okay. Let's see. Now I just screwed up my presentation. I can't see it. There we are. Okay. So, oh, damn it. Sorry. My computer's giving me trouble here. There we go. Okay, so that was slide 6. Let's go to slide 7. Case A is easily explained then. All we have to do is hypothesize that both particles carry the same instruction set. If both particles carry the same instruction set, then they will, then what do we get? We get, for instance, if both particles carry RRG, then, well, the only important thing, right, is that if they carry the same instruction set, we will get, if they're both set to the same number, we'll get the same flashes. If they're set to different numbers, then we, oh, sorry, case A. Sorry, case A is the same numbers. If the switches are set to the same number, you will obviously get the same color flashing because they're both carrying the same instruction set. That's all we need to know. So slide 7 just points out that easily explains case A. If the instruction sets are the same, we will always get the same color on both detectors and never get different colors because the instruction sets are the same. Make sense? Okay, so there is an important question here, and the question is there any other way to do it? Can you explain the results in any other way? Case A results any other way. And it's just that Merman issues the challenge to try to find one. He says he can't prove there isn't, but he opines, and I will as well, that you will be very hard-pressed to find any other way to do it. So you're free to try. And if that's the case, of course, then it has to be instruction sets. But can't prove that. You're free to try to find some other way to do it. Einstein famously thought that there must be, and we'll get to that. Thought that there must be some other way to do it. So here we go.
I might have one. The detectors have nothing to do with the particles, and when they are set to the same number, they just light with the same color.
Okay. Oh, good. Okay, that's a very good observation. So now, so here's the thing about that is that if you want to assume that they flash the same color simply because they're set to the same number, then they have to talk to each other and know that they're set to the same number, and B, decide which color light they'll flash, right?
The second part is very easy once you establish the first one, and there's nothing in your experiments to say that the first case doesn't occur. You just told us that there's a machine with a detector and some numbers, so could totally be the case.
You broke up a little bit there, Shamash, so I didn't catch all of it.
Okay. The second part. So the fact that they agree.
You are sorry, Shamash. You're breaking up. I don't know if you're in a bad place.
I'll leave and come back.
I think it was only breaking up for you,
John,
actually,
I
John.
think it's you and not Shamash. We can all hear him clearly.
Oh, is it me? Oh, sorry. Wow. Okay, that's interesting.
I think it might be. He didn't break
Am
up
I
for
back?
me at all.
Am I
No,
back?
apparently it was me, Shamash. Sorry. Everybody else is telling it was me. Am I breaking up from time to time?
No, you're not breaking up, John, but
We can hear you.
You were losing him for some reason. But okay.
Yeah, that's weird. Okay.
We have a case of quantum entanglement here. Let's go. This is so fitting.
Oh, that's very weird. Yeah, I'm still getting Shamash broken up. I don't know why that is. Anyway, Let me just say, so Shamash was saying maybe it's just that that the detectors, when they're set to the same number, they just flash the same color, and I think that's a good point, and it makes an
John?
important point. Yeah, go ahead.
John, would you like to leave the room and come back for a minute? So
Am I breaking up now?
He's fine for me.
No, John's fine for us, but
I
there's
think he's
something
just
wrong with
messing with
confirmation.
you. I think he's just messing with you, John.
John, if I
possible,
could
yeah.
just respond to Shamash's throwaway comment.
Okay.
He said that this must be a case of quantum entanglement. And,
Yeah.
I want to point out that I think that quantum entanglement serves as the answer to all mysteries in science. If there's something that can't be explained, it can always be explained as a consequence of quantum entanglement.
You're
And
kind
that
of confusing that with miracle or magic, maybe.
Yeah, exactly. So one of us is confusing it, right? So I just want to make that point, and we can move on.
Yeah, well, so I think related to that point, Benjamin, I think Shamash makes a really good point. It is, what if the detectors simply talk to each other and agree on what color light they're going to flash this time, if their switches settings, so they communicate. They say, our switch settings are the same. Let's flash red this time, right? They couldn't do it all the time because that would violate kind of the unbiased nature of the data. But they would have to, first of all, ascertain that their switches were set to the same setting, and then decide which light to flash. And that could happen. I mean, I'm not saying that to rule it out. I'm saying that could happen. And it's an example of what we call a loophole in these kinds of experiments. What if the detectors are communicating with each other and deciding what to flash, which has nothing to do with the particle? Oh, our switches are set the same. When we get our particles, let's ignore the property of the particle and simply flash red or green. I think that's what you're suggesting.
Yeah, but that's been ruled out by setting the switches too late for that to happen, right?
Yeah, I didn't want to actually say that yet, but I mean, I don't mind you saying it. But I want to point out that I think it's a really good point that Shamash made. It's an important point, and it's an example of what we call a loophole in this kind of experiment. And then we'll get back to that and talk about what Ben just said, how physicists try to address loopholes like that. So for now, let's just say, yes, good point, Shamash. Let me assure you that the idea here is that shouldn't matter, that either that it couldn't happen or that it shouldn't happen or anything, but then we can talk about how we know that, why we think that, etc. We'll get back to that. Okay, so that's slide 7. We've now easily accounted for observed flashes being the same when the switches are set to the same number. But what about case B? What about when the switches are set to different numbers? Well, let's just look on slide 8. I show the results for 2 representative instruction sets. If both particles carry so type 1, where they're all the same, I'm using RRR, but I think you'll see that the same kind of results occur with GGG. And type 2, I'm using RRG, but I think you'll see that the effective results from any type 2 instruction set are the same. And by that I mean this. If the instruction set is RRR, then in both case A and case B, you always get both red lights flashing. Right? That's what you always get. If the instruction set is RRG, then in case A, when the switch settings are the same, you get red when it's 1-1, you get red when it's 2-2, and you get GG when it's 3-3. Both particles are carrying the instruction set RRG, so if they both encounter detectors set to number 3, they'll both flash green. Otherwise, they'll both flash red. So that's the case A part of the RRG instruction set. Different numbers, the case B analysis for the type 2 instruction set is really the only one that where you have to, spend a moment or two thinking about it. If the two detectors are set to 1 and 2, then you just look at the instruction set and you see that you'll get red, red. If the two detectors are set to 1 and 3, you just look at the instruction set and see that you'll get red, green, etc. Go through that. 2-1 also gives you red, red. 2-3 gives you red, green. 3-1 gives you green, red. 3-2 gives you green, red. And you'll notice that of those 6 case B switch settings, 2 of them produce the same color, 4 of them produce different colors. And I think you might be able to see that you're going to get that same result you're going to get regardless of which type 2 instruction set. If you have a type 2 instruction set, then in case B, where the switches are set to different numbers, you're always going to get the same color 1/3 of the time and different colors 2/3 of the time. Does that make sense? Let me just let all that sink in. The important thing here is looking at the bottom 6 entries on the right, the type 2 instruction set, case B switch setting thing, and noting that every time you have a type 2 instruction set, you get the same color 1/3 of the time. That is the hardest thing in this entire analysis. If you get past that, you're home free.
This is a classic case of what mathematicians call without loss of generality. So if you switch the names between G and R, the same mathematics applies. It's just that you get GR instead of RG and GG instead of RR. Everything else will be the same.
Right. The statistics, as far as how often you get the same colors, are unaffected by the fact that they'll occur in different places or something. Yeah. No, what did you call it, Shamash?
It's a classic thing. They will write WLOG, so without loss of generality.
Nice. Yeah, right. I like that. I never say that, but I do know that.
You've definitely seen it before, I'm sure.
Oh, yeah. No. I just never say it. It's going to be, I think today, what you've just done for me, Shamash, is you've added that to my vocabulary, like entailment was added to my vocabulary a year or two ago.
Every 100 episodes, we add one to vocabulary.
Yeah. Okay. So there's what we predict in case B, right? We already took care of case A. We see that the instruction set covers us. Case A, it does the right thing. What about case B? Well, here's the prediction. In case B, type 2 instruction sets produce the same color 1/3 of the time. Type 1 instruction sets produce the same color all of the time. So I invite you to imagine what the result of an experiment will be. I mean, if you did this over and over again, and then you simply asked, how often, when the switches are set to different numbers, do we get the same color? Well, okay, it has to be at least 1/3 of the time, because even if all of the instruction sets were of type 2, you'd get the same color 1/3 of the time. If you throw in some type 1 instruction sets, which always produce the same color, then the net result is that you're going to get the same color more than 1/3 of the time. So let's just, we'll just keep that, and then we'll look at the last slide, really, the last slide of the presentation here. Oh, no, it's not quite the last slide of the presentation. So here's the fully general predictions. If the switches are set to the same numbers, case A, The prediction is that you will always get the same color, never different colors. If the switches are set to different numbers, case B, then at least 1/3 of the time you'll get the same color, and no more than 2/3 of the time will you get different colors. You get 1/3 of the time you get if you never have type 1 instruction sets. But if you throw some type 1 instruction sets, then you'll get the same color more than 1/3 of the time. 1/3 is the minimum frequency that you'll get red, or green, green.
Quick clarification. We have this open interval now between 1/3 and 2/3 because we don't know whether the two particles are the same one or not. If we add that, we would know exactly that it would be 1/3, right?
Well, the hypothesis is, I don't know what you mean by same particle. The hypothesis
I mean,
is
I mean the two particles, the one that goes to A and the one that goes to B, we don't know whether they have the same instruction set or not.
No, that's what I thought you were saying. No, that's the hypothesis, is that we are explaining the results by saying both particles carry the same instruction set. That is the hypothesis.
Okay, but if they are, why is it that now we have an open interval and we're not really sure? Can it be 1/2? So if it's between 1/3 and 2/3, how do we get that result?
I think you're misreading the table. Forget about the 2/3. The only important thing is that our hypothesis ends up saying that the two detectors should flash the same color at least 1/3 of the time in case B. That's all. The less than or equal to 2/3 is simply an entailment of the fact that more than one, that at least 1/3 of the time you're going to get the same color.
I get that, but we just saw a table that says exactly 1/3. I'm just wondering where that bigger than came from.
Oh, right. So let me say that again. I've said that, but I know it is, you have to be really clear on that. If all of the instruction sets are of type 2, if they're all of type 2, then you'll get the same color 1/3 of the time. If some of the instruction sets are type 1, which always produce the same color, then you'll get the same color more than 1/3 of the time. So, for instance, suppose all of the instruction sets were of type 1. If all of the instruction sets were of type 1, you would always get the same color.
I get that. And then when type 2 happens, it's 1/3 of the times, right?
So,
if it's all type 2.
No. So if it's all type 2, it's 1/3 of the time. If it's all type 1, it's 100% of the time.
Now I get it. So there needs to be a third column in your table that says a mix of both, and then we'll get that bigger than and smaller than. Okay, I get it.
Yeah, right. So the greater than or equal to just reflects the fact that we don't know what the mix of instruction sets is. But regardless of what it is, it'll always be at least 1/3 of the time.
Got it. Thanks.
Yeah. No, that's a good clarification. So the
actual experiment mixes cases where the instruction sets are of type 1 and cases where the instruction sets are of type 2. And
we don't know.
The minimum possible case is that you get all type 2, in which case it's 1/3 of the times.
That's
and it will
right.
be always bigger than that number because there's no way that you can get less than that.
That's right. And so that's the important thing is that the smallest, in case B, you will always get the same color at least 1/3 of the time. And that's all we need to know, because I'll just remind you on slide 10 of what we actually observed. We observed in case B that you get the same color 1/4 of the time. That's what actually happens, is that you get the same color 1/4 of the time. Our hypothesis of instruction sets has an entailment that can happen no less than 1/3 of the time. But it does happen only 1/4 of the time. So this is a case where an entailment of the hypothesis, our hypothesis is both carry the same instruction set. One entailment of that is that in case B, at least 1/3 of the time you'll get the same color. And what actually happens is 1/4 of the time. So that's just a conflict between a strict entailment of our hypothesis and reality. And when the entailments of a hypothesis, of a model, conflict with reality, reality wins. So the model's wrong. The hypothesis is wrong. There aren't instruction sets. So and that's really pretty much the end of the thing. I just want to end with how Merman ends his paper. I haven't yet brought up anything, but this will lead us right into the conversation that Benjamin is itching to get into, and we will get into it. Now, here's what Merman says at the end. He says, so the question now is, okay, instruction sets cannot explain the results. How do we explain the results? How are we going to account for these results? Merman says, I shall not describe how contemporary physical theory accounts for the behavior of the device, except to note that although in its own way, the explanation, except to note that although in its own way, the explanation is very simple, it's also far from obvious. So we have a theory, we have a physical theory that provides a very simple explanation for these results. But it is far from obvious. Far, far, far from obvious. And some might argue, I know at least one person who does, and I think I would as well, it's hardly an explanation at all. We have a theory that makes this prediction, but it's not at all clear what the theory is doing, what's happening underneath. But in quantum mechanics, a common phrase is shut up and calculate. And if you shut up and calculate and you use quantum mechanics provides an absolutely trivial explanation for why you get these results that people 100 years on are still scratching their head over and saying, but how can that be? And Einstein was famously one of the first people to really throw down the gauntlet along with Podolsky and Rosen in a paper that they wrote in 1935 saying, here's why this is obviously nonsense. And Einstein convinced a lot of physicists that there had to be something more going on than what quantum mechanics provides. But let me just finish Merman's quote. He says, the explanation is very simple, but it's far from obvious, and some might argue hardly an explanation at all. Instead, I only emphasize again that we live in a world in which such a device can be built, and that nature is stranger and far more wonderful than we had once thought or could possibly have imagined. He says, ponder the device a little more, ponder the results, think about your possible explanations. If that seems too extreme a conclusion, and I like just leaving it here, quantum mechanics does provide a very simple, quote, accounting for it, but it hardly explains it for reasons that we'll get into, because it really requires you, and maybe I should have said this at some point, I will now, quantum mechanics requires you to accept the truth that a particle doesn't have a property until it's measured. It only has potentials for different, I shouldn't say it doesn't have a property. So a particle, you can talk about the properties that a particle can have, but you can't know the value of that property until it's measured. Einstein would have said, well, that's just because you haven't measured it. Quantum mechanics says, no, it's because the value of that property doesn't even exist until you measure it. Particles do not have real properties until they're measured. And that is to say that There's no such thing, it's often said this way, that there's no such thing as local reality. You can't look at a particle and say, okay, that particle is going to make the red light flash if the switch is set to setting 2 or whatever you want. You can't do that because the particle doesn't have the property that would make that happen until it's measured. And that's weird. That's weird. I don't like it. Benjamin really doesn't like it. Lots of people don't like it. But I'm done. Benjamin, before I let you launch into your thing, let me just ask if there are any comments or questions or anything else on the presentation. Steve,
No,
I
I
saw
think
you
it's
unmute
pretty
first.
I obviously am going to preface this by saying I know nothing about this subject. I am utterly ignorant, but fascinated. So this question, one of the responses might be, your question just doesn't make any sense, but I'll ask it anyway. So I've read about quantum, this experiment before, and it's a subject I'm interested in. I just have no background in the subject. And I've always heard it stated the same way you stated it, which is that measurement is the thing that fixes something, to paraphrase, right? And what I'm
Right.
trying to understand is, can it be something other than measurement? In other words,
Yeah.
you've devised this device which somebody looks at and they see a light. That's the only reason it's measurement. It's measurement because it's a device that enables a human to record a result. But are there forces in the universe? Is there a thing that is analogous to that machine? There's no human observer. It's just something out in the universe, a particle, an electromagnetic force, a field that impacts a quantumly connected particle, I don't know, 10 light years away, and then causes the entangled particle to do something. Because I don't get how it's just measurement. What if there's no
Yeah.
one looking at the machine? What if the
No.
machine doesn't light up? It just impacts the particle in some way, and there's no observable measurement that a human can write down. That's the essence of my question.
So let me just say, first of all, that is an excellent question. It's probably the question I would, if I had slipped you a 20 and asked you to ask the first question, that's probably the question that I would have asked you to ask.
Wait, you're paying people for asking questions? I never got. What is it?
You know what? It just hit my Venmo. You weren't supposed to tell anyone, John.
Yeah, no, it's really a good question, and it's really at the heart of this whole measurement. I mean, some people really have kind of maintained that human consciousness has to come to bear in order for the property to become fixed in these things. I think that's crazy, and I don't. My personal feeling is that measurement ultimately, and I think a lot of physicists, certainly Roger Penrose, I think, believes this, that measurement is really just a result of interaction with other things. When a system interacts with other things, at some point, this property of the particle is going to be called into the service to determine what happens next. And that is a measurement, if you want. It's a way to collapse the wave function without invoking human consciousness in the process. And I'm sure we'll have more to say about that as well. But now that's a really good question. You asked another part of it had to do kind of with what we call spooky action at a distance. And as far as that goes, let me just point out, I haven't said anything yet about spooky action at a distance. Indeed, all this is really, I talked about loopholes. Shamash asked a good question earlier about loopholes. The first experiment like this that was done on a tabletop by a guy, John Clauser, up at Berkeley. When I was there, and I didn't know that he was doing this at the time, but he did an experiment which was just simply to test the predictions of quantum mechanics for two what are called entangled particles. I can now at least say that. The particles we're talking about here have to be entangled, which means I know a property of the system of particles that can be realized by having each particle itself in a different state. And the most common thing is to say that these two particles are in the quantum singlet spin state, which is to say that I know that the net spin of this system is zero, and that can happen because the first particle is spin up and the second one is spin down, or the first particle is spin down and the second particle is spin up. And so the quantum state is an equal mixture, a superposition of the states in which the first particle is up and the second particle is down, and the state in which the first particle is down and the second particle is up. The quantum state is a superposition of those two states, which don't tell me anything about the state of one of the particles, but do assure that the net spin of the system is zero, because that I know from the process that created them. And so then the question is, the question hinted at when you start talking about spooky action at a distance things is how does that, how is that somehow communicated, et cetera? And we'll have more to say about that as well. So yeah, really good opening question. Go ahead, Ben.
So I think what's clever about it is he's enumerated every possible combination of the 3 bits of hidden variables in those particles, and shown that the real world correlations you actually get, the 1 count, the 1/4, can't be explained by any scheme of local hidden variable instructions, right? Of hidden variable instructions.
I wouldn't go so far as to say this shows that, but that is the argument. And it does hinge a little bit on believing that there is no other way to do it except instruction sets. And effectively, that's what John Bell did with Bell's theorem. When Einstein wrote his objections, he didn't yet know about what Bell later proved, which is to say that quantum mechanics, that the predictions of quantum mechanics, full stop, are incompatible with local reality. If you believe quantum mechanics is right, then you have to accept the fact that there is no such thing as local reality, because quantum mechanics makes predictions, as it does in this case, that cannot be explained by any model, not just instruction sets, by any model that invokes local reality, that the particle has these properties before they're measured.
Yeah, it doesn't Bell's effectively address a triplet? Doesn't he assume that, well, not assume, but show that that the predictions of quantum mechanics that it makes and that we see in every experiment we ever do, so it's a good reason to believe quantum mechanics, require us to let go of the idea of locality plus realism plus like freedom of choice or something altogether?
Well, I don't think I'd go so far as to say that all predictions of quantum mechanics do that, but it's just the predictions in this particular case are really nothing more than the predictions of quantum mechanics. And if this is wrong, then there's something deeply wrong with quantum mechanics. I didn't finish my story, and then we'll move on. Sorry, I'm talking too much here, but a few things to say. John Clauser did effectively a version of this experiment, and not exactly even the experiment that this is referring to, but a version of an experiment testing these kinds of things, which allowed for communication between the detectors. The detectors could have communicated with each other, but all he was doing, quantum mechanics doesn't say, if the detectors communicate with each other. It just says, here's what you're going to get. And he just did the experiment. A lot of people told him not to waste his time, that he'd look like a kook doing this experiment, because everybody knew what he was going to get. There was no real controversy about it. Quantum mechanics made a simple prediction. We knew what we were going to get, and the only thing was that Einstein had a problem with it. So Clauser thought, well, let's try it and see. And Clauser just did this experiment that everybody told him not to because everybody knew what he'd get. Got the result, and he was hoping not to get that result. He was hoping to show that quantum mechanics was wrong because he would have gotten the Nobel Prize very quickly after doing the experiment if he had been able to show that quantum mechanics was wrong, which he would have done if he had gotten a result other than the result he got. And then 50 years later, he got the Nobel Prize for doing nothing more than showing that quantum mechanics gives the right prediction. And the history of how we get there is, I think, really interesting. It turns out that he would have gotten the Nobel Prize no matter what the result of that experiment was. And I just think that's completely fascinating. Doing an experiment that everybody thought he shouldn't do because everybody knew the result he would get, and he got that result. Okay, sorry. Really too much. Bert, you've been trying to get in.
Well, I'm trying to think of what experiment I could do that no matter what I get a Nobel Prize.
Yeah, boy, me too.
But all right, so I think I caught on here the 8 possible states, 2 for option A, 6 for option B, right?
Mm-hmm.
And
well,
then
no.
question-
No, you're talking about instruction sets. Type 1,
Oh,
there's 2
sorry.
in type 1 and 3 and 6 in type 2. Yeah.
There we go. Okay, so in the 2 in type A are 100% same. The 6 in type B are 1/3, 2 out of 6 same.
Right.
And you're saying the results that we get is 1/4, which would be an equal mix of type A and type B of the 8 possible options.
Oh, I think maybe you're misinterpreting. So the question is, when in case B, when the switches are set to different numbers, how often do we get the same color light flashing? And you see that if all of the instruction sets are of type 2, I'll get the same light flashing 1/3 of the time.
Mm-hmm.
If all of the instruction sets are type 1, I'll get
Right.
the same color all of the time. And so no matter what mix I get, I don't know what the instruction sets are, but no matter what mix they are, there can be no fewer than 1/3 of the time
Okay.
will I get the same color.
But did I understand correctly that the experimental results produce 1/4 of the time?
That's right.
Okay, so then does that mean that the instruction sets are merely equally distributed among the 8?
No, it means a strict entailment of the assumption that there are instruction sets is that you will get the same color no fewer than 1/3 of the time. But what we actually see is 1/4 of the time. So the only logical conclusion of that is that the model, the idea that there are instruction sets, is wrong because a strict entailment of that conflicts with reality.
Right. So if it was an equal distribution of the 8, it would be half the time because it'd be 4 out of the 8.
Is that? Let's see. I'm not sure. I think I'd have to work that out. Frankly, I think that's not.
Well,
I think it's 5/9 or something. If you actually work that out with an equal mix.
No, there's 8 possibilities. The 2 and A are yes. The 6 and B are 2 yeses and 4 nos. And together that's 4 yeses, 4 nos.
I don't know why my brain isn't working that quick. Maybe Shamash or somebody else who has a mathematical brain working this morning can verify that. You might be right, Bert. I don't know.
Sorry, I wasn't listening. What is it?
Well, so Bert is trying to work out if there were an equal mix of type 1 and if all 8 instruction sets occurred with equal frequency. This is a simple probability calculation. How often would the same light flash? So it's simply this: 1/4 of the time, the same light would flash all the time, and 3/4 of the time, the same light would flash 1/3 of the time. So that's all we need to know, right?
Multiply that together, you get 1/2.
How did you get 1/2?
3/4 of 1/3
I think
Three
that's right.
fourths
plus
of
1 of
one.
I think you're
1/4.
right. Yeah.
Oh, so 1/4 plus 1/4. Yeah. Okay.
Right, right. And then if you look at it even simpler, you see that 4 out of the 8 are yeses and 4 out of the 8s are not the same.
Yeah. So let's see. You're looking at the table on. You're looking at the table on slide. Oh shoot, which is that? Slide 8.
I'm unsure what that number means. I mean, we are
Yeah.
assuming that there's two cases, red and green, and we are assuming that there's no bias to red or bias to green. So that 50% number is what we started with. It's not something that we just discovered.
Right. So all I'm saying is if they were equal distribution, I was trying to see if I could get to 1/4, but I can't.
Right.
It's interesting that the A cases represent 1/4 of the half, and the B represent 1/4 of the half, and that's I'm just trying to do some mathematical, you know,
It's funny. I'm resisting this only because number one, we have to restrict our attention to only case B, right? In case B. So what is it? 1/4 of the time, you always get it, and then 1/3 of the time. No. Three quarters of the time, you get 1/3. Yeah. No, I think that. No, it's 1/4 percent. Yeah, I'm sorry.
Okay,
I have to think.
Yeah.
I think you're right, but somehow the only reason I don't is because I don't remember ever calculating a frequency of a half for this, my brain is just too flustered right now to go through it. I'm getting the same result you are, Bert, but I'm thinking that we're both making the same mistake. Maybe I'm wrong.
Okay. I see. Actually, I wasn't looking at page 8. I was looking at page 6, where there are the 8 instruction.
At any rate, let's not linger on that now. I think it is clear that I think it's clear that the instruction set is incompatible with the observation that 1/4 of the time you see the same thing.
It's probably just worth noting that something interesting only happens when you have different switch settings. Nothing interesting happens when you have the same switch setting.
Right.
So that's restricting what you're looking at.
Well, it depends on what you mean by interesting in a way, right? I mean, the thing is, in case A, when the switch settings are the same, it's just so obvious that, well, they're just the same instruction sets, right? I mean, you do that, you say, well, fine, that works, done, right? But then the problem is that hypothesis is incompatible with the results in case B. That's really the meat of the argument. So, yeah, it's good. I don't want to delay. Benjamin, I'm sure you're itching. Would you like to take the stage for a few moments? Maybe he's having a sandwich. Lunchtime in Colorado.
To ask the questions. Has everybody asked the questions they want to ask?
I'm sure there'll be more down the line. Certainly anybody's welcome to. I don't know. I haven't been looking at the chat. Robert's got a lot of stuff to say. I don't know if he wants to come up on stage. Maybe he's not here anymore.
We have Catman saying the problem with local reality and quantum is decoherence of quantum states. The phase transition happened too fast to stay stable. Hopefully someone can correct me here if necessary.
Yeah, decoherence is a thing in a lot of situations, not probably in these experiments, because when experiments like this are done, they're typically done with the particles flying through a vacuum. We don't think the particles really are interacting with their environment on the way from the box that produces them to the detector. I think even Benjamin would probably agree that decoherence isn't really an issue. That becomes more of an issue in quantum computing when you've got these qubits that you need to preserve in their state, but you also need to have them in this machine, confined with stuff that's going to interact with them. And to Steve's earlier question, that whole subject of decoherence really is, I think, ultimately kind of connected with the measurement problem in quantum mechanics, that when a system is interacting with its environment, there are effectively little measurements going on that change its quantum state. I think most people would agree with that.
John, can I ask a question related to what you just said?
Mm-hmm.
So it seems clear from what I've read and what you've said, even though we're focusing here on two particles being entangled, it doesn't have to be two, right? It could be three
Right.
or more. And so in the example you gave, it was sort of a binary thing, like spin either up or down. So two-part question. When multiple particles are entangled, are we still talking about binary states, or are there more complicated states? And second question, is when they refer to strong entanglement versus weak entanglement, does that have to do with whether it's just two particles or a bunch of particles?
Okay, well, so in answer to your first question, there are some people who think that if you really follow quantum mechanics to its end, there is just the wave function,
Right,
the
of the
wave
whole universe.
function of the universe, right? And everything in the universe is potentially and almost surely entangled in some way. So yeah, it's things can have more than two entangled particles. And in fact, the last of Merman's 3 papers that he's written on this topic, which is in some sense the simplest, because the measurement is so simple. You get the result from just analyzing a single measurement, involves 3 particles that are entangled and 3 detectors that have, I think, just 2 switch settings. So, that's a different version of that. In answer to your second question, my answer is I don't know. I'm not even sure I know I haven't looked into the idea of weak versus strong entanglement. Maybe somebody else has. Hanson. Maybe Hanson wants to come on stage. I'll bet he has something to add here. Hi, Hanson.
Hey, John. So the weak versus strong is just the coefficient in the this tensor product summation. The and the Bell state is the maximal for the 2 particle maximally entangled.
So Hanson, let me just ask you a question. Is it about, so in the singlet state, you have this kind of maximum entanglement in the sense that the wave function is the sum of 2 wave functions that have each particle in a different state, kind of, whereas maybe weak entanglement would be some superposition of that state with some non-entangled states or something, some single particle states. Is that the idea?
Maybe, yeah, you can probably do this convex combination of these things, but the it's easiest way to see this is just basically it's you have the 2 coordinate, right, or bases, and then the coefficient on these bases. If it is evenly distributed, if the coefficient is all equal, that's a maximally entangled. But if it's a bias, lopsided, let's say, one
So
is
if it's
0.9 or 99, and then the
0.9 spin up, spin down, 0.1 spin down, spin up, or something.
Right.
Okay.
Actually, it should be more like
Yeah.
square sum of the
Yeah, square root. Yeah, right.
So
John,
basically,
are you able to translate that into
Yeah,
English?
I think what Hansen is saying is just in the singlet state is a superposition of equal amounts of up down with down up. But if you make a superposition that is more up down than down up, then that's a weaker entanglement. Is that fair,
Right,
Hanson?
right, yeah.
Yeah.
So if you choose, if you let the coefficient distribution move to 0, 1, right? And that would be
Right.
completely disentangled. And
Right.
then
So
if
so
it's
in the mathematical expression, you really write that the wave function is 1 over the square root of 2 times spin up, spin down, and 1 plus 1 over the square root of 2 times spin down, spin up. And the probabilities of each one of those is the square of the coefficient in front of them. So maximum entanglement comes when those coefficients in front of the two are the same, and as they approach not being the same. If, for instance, if the superposition was 1 times spin up, spin down plus 0 times spin down, spin up, then there would be no entanglement whatsoever.
right, and then so it's the uniform. The more uniformly distributed, the more entangled it is. And basically, it's the same. You can use the same the concept as in entropy. So the highest entropy is the most entangled because it's most uniformly distributed. And if it is lopsided distribution, is the low when you have the lowest entropy.
Okay.
So the entropy actually measures the entanglement, the degree of entanglement.
Okay. Well, that's good. I thank you for educating me. I'm not sure how fruitful that it is to continue down that for the audience in general. I do want to get to Benjamin once we've exhausted questions on the presentation, which I think we're getting close to.
I'm curious about the square root
Well,
relationship
so it's
there.
just that in quantum mechanics, the probabilities are generally the square of the coefficients in front of the wave function components. And so if you have a superposition of states that you want to be equal probability, that means that the actual mathematical wave function is 1 over the square root of 2 times the first wave function plus 1 over the square root of 2 times the second one. That means that the actual state is equally likely to be either one of those because
Okay, gotcha.
it's not worth worrying about. That's just the mathematics of quantum mechanics. That's the shut up and calculate part, I guess. Benjamin, you wanna take it away? Do you wanna? I don't know. You probably have almost prepared some remarks in your brain.
I have always have remarks prepared. You want me to respond to your presentation? So I will respond first by just expressing a moment of silence for all those
Yeah,
students who took
go
this
go ahead.
in school. I think the Merman paper would be very frustrating for me as a student because it assumes all of the things. Steve is here. Steve Krohn is a lawyer, right? And he's familiar with the trial. So I think that it moves immediately to the punishment phase of the trial and skips over the fact-finding phase of the trial. And for that reason, I think it's really, really conclusory. But more generally, I'm beginning to, after studying this for 3 years now, I'm beginning to think that Bell's paper is unfortunately very reductive. And by reductive, I mean he uses an inequality. He says that if it's greater than 2, it means this, and if it's less than 2, it means that. That means that all the experiments in the world you can do reduce to being either greater than 2 or less than 2. There's really only 2 options. And 2 options is not a very profound prediction. If I were to predict that tomorrow is going to be either um, sunny or not sunny, like I'd have a 50-50 chance, maybe even better than a 50-50 chance on most days of it being sunny. And I don't think anybody would give me a ton of credit for being right once.
on that kind of binary prediction. Now, um, is it the case that the experiments demonstrate that it is always greater than 2? Well, clearly they don't. And so we get into very quickly what amounts to a no true Scotsman fallacy, which is any experiment that shows that John Bell was right is a properly conducted Bell experiment. And any experiment, including the one that John Clauser writes about at Caltech, which took place, I think, at Harvard, that failed to find that conclusion is not a proper test. And that's just a no true Scotsman fallacy.
And that was,
So
well, when you finished, so
so
many
I
things to
am
object to.
yeah, I'm starting to think that we have to get at this from another angle, an angle that doesn't require us to deal with John Bell's argument, because I think John Bell's argument is just not well stated. It doesn't make a prediction. If it had said, like, if you do this experiment, the numbers will converge on 2, 0.9, 0.7, 0.3, 0.4, something really precise. That and then we did the experiment, and then it converged on that number, like, very precisely with 14 decimal points of accuracy. That would be something. But to have converged on an inequality, when the experiments fail to publish the raw data of their experiment, and they just say, "Trust me, bro, this is what the data said." I think that's the fact-finding portion of the trial is very much, leaves a lot to desire. I think even Steve Krohn would recognize that if John Clauser is not willing to let other people look at his data, that he doesn't have much of a case. And if that's true for Lena Aspe and also for Zeilinger, that starts to look like a pattern. I wouldn't call it a conspiracy, because I don't know how much those people communicate with each other, but it's definitely a pattern. So what I'm thinking as an alternative is that we look at the behavior of a single photon going through 2 polarizing filters at some distance, and where the polarizing filters are rotating very quickly.
Well, hang on a minute, guys. John, are you happy to let Benjamin go on this massive diatribe? First, he's written off Mermin's paper by an appeal to Steve's authority as a lawyer without attacking any of the logic of Mermin's paper. He's then gone on to do some drivel about experiments and strongly state Bell's inequality. And now he's about to start making up some experiment that I've heard the premise of is already been tried and is fundamentally flawed anyway. So do you want to break things down one at a time? I thought Ben was going to respond to the paper. What is wrong with Mermin's argument about instruction sets? I don't know if Benjamin's understood the paper. You might want to test that. That might be interesting.
Well, this was my thesis yesterday. Part of the reason I did this today was Benjamin and I were talking yesterday, and my thesis to him was that I didn't think he fully understood the paper, because he does make arguments, I think, sometimes that seem to miss the point of Bell's theorem, which is, I think, illustrated in this paper.
So why don't you publicly test his understanding of this paper? Because I think if he's going to qualify to come here and try and make arguments and other suggestions, we should check. The audience should know whether he understands the material. So why don't you test him live, or I will, and see if he's actually understood this paper? Because I don't think he has. I think he's just sat and listened to everything you had to say and waited till his chance to jump in and say his stuff. But I don't know, but I just don't know if he understands Mermin's paper.
I think that's not a bad
paper.
I think that's not a bad idea, and I am kind of motivated to do that. But I also understand that Benjamin's problem often is not really fundamentally about, what quantum mechanics predicts. I think he would agree that quantum mechanics makes predictions for outcomes like this that cannot be explained with any theory that involves local reality. I think he agrees with that. That's what Bell proved. And so let me just say, I think his problem is often more with the fact that he does think that it's some mixture, some superposition of quantum mechanics is wrong, and 2, experimenters are not telling us the truth, either willfully or, for some other reason. Is that for? So I think it is a good idea, Benjamin, for you to maybe steelman the paper, or just tell us that you accept it. I think you accept basically the paper. I think you accept the predictions of quantum mechanics are incompatible with with local reality. Maybe I'll just stop there. Is that fair?
I would say that the paper is a lot of decoration around one simple formula, which is down there at the bottom left of the paper in the appendix section.
No, wait a minute. You're talking. Oh, you're talking. Okay. No.
And
So
all you need to know is that it is cosine theta.
well,
And
okay. So then I have hold on a sec, Benjamin, because I really think that what you just said does reveal to me that you do not understand the paper, because there's
his opinion
no
is really
need.
important for people listening, that his opinion only matters if he can demonstrate that he is fully absorbed. It took me a lot of mental effort over the last 2 hours to sit and stare at your fantastic presentation and really understand it. And I think I'm only a third of the way to really internalizing it. I do get the point, the logic of it. I think it's fantastic, and I really thank you for doing it. I think you should test whether he's done that. If he hasn't, he can't comment on the paper, because until you've had the aha moment about then you can't comment on it. It's nothing to build on, and then his opinion doesn't matter. We should move on. You set the whole room up, putting him on a pedestal, like he's going to be the guy whose opinion you're going to ask at the end and all that. But test him, see if he understands even this basic paper that you spent all this effort teaching us.
I think I will do that now, because I think, Benjamin, that by going to the appendix and the cosine squared thing, which goes to a pet, a pet point of yours with Malice's law and all this, you have to be missing the point, because the paper depends in no way, the conclusions of the paper depends in no way on that. He's telling you why quantum mechanics makes the prediction it does. But if you understand that the results of this experiment, because of the predictions of quantum mechanics, are that 1/4 of the time in case B, you will get same colored lights, and that you cannot explain that result. That is the result predicted by quantum mechanics, and it cannot be explained with any local reality, with any theory based on local reality. It's the prediction of quantum mechanics. It's what we see in experiment, and it cannot be explained with local reality. All of that is just 100% solid, and I know that you take issue with portions of that. But let's take them piece by piece. First of all, steelman the paper. Tell me about the case B thing.
The paper is describing the difference between two predictions, which are on my PTR since our last conversation. One is a distribution of probability over theta. That's the rotation of.
Yeah, so you're not steelmanning the paper.
Theta,
yeah,
Ben. There's no theta in this paper.
Yeah.
So try again.
Oh, there is.
No, there's not.
There's no theta in
There is no theta in this paper. This paper simply tells you what you see what the predictions of quantum mechanics are.
Ben, look,
and
the argument is in John's Google Drive slides, right? Regardless of any additional information in the paper, the argument in Google Drive slides that was linked at the top of the room is a complete argument and a very compelling argument. Attack that argument coherently, or stop wasting everybody's time.
Okay, so the question now, and this is a proficiency question, is whether or not the term theta appears in the Merman paper or doesn't.
Yeah, no, I think Ben is right.
It does not appear in the Google slides. Search for it. Anybody in this room can search for it. It's not in the slides. The slides contain the complete argument. Attack the argument in the slides, or that you don't need to go beyond the slides.
I don't intend to attack the argument, because everything about this argument is correct. It is just
okay. Well, then that's that.
That's the topic of the room. So fine.
If you use it, right, exactly, and I'm commenting on the topic on this paper, on this Merman paper. If you use the cosine theta, then you
No,
get
but
this
Benjamin, I'm sorry,
sinusoidal.
I do have to stop you. This is the paper deals only with the predictions of quantum mechanics, and yes, there is some math under it. But all I'm telling you is what the prediction of quantum mechanics is, and showing you that it's incompatible with instruction sets. That's what the paper. That's what my
There's
slides
no.
rigorously prove. Now, you can take issue with that being the prediction of quantum mechanics, but I don't think you do because you know that
Oh, I
is right.
don't. I
If you
don't.
take
Yeah, I don't take.
if you
I don't
take
really
the
take issue with the paper.
if you take the cosine of
Didn't I make?
120
Wait.
degrees and square it, you get 1/2. That's
Yeah.
really the only place that it comes in here. But there's no, if you're taking issue with the cosine thing, what you're saying is that your thesis is that quantum mechanics is wrong. And that's fair. I will allow you to believe that quantum mechanics is wrong. I won't allow you to say that the argument in my presentation today has anything to do with an angle. It doesn't. It's simply comparing a prediction of quantum mechanics to reality and to the entailments of a locally real model attempting to explain those results.
Cool. I mean, what Merman is doing is he's trying to reframe Bell's argument in his 1964 paper for an audience that is uncomfortable with the mathematics in the paper. So he has
That's right.
done it as a statistical presentation without using the formalism of the quantum notation.
That's
That's
right.
fine. But the paper does nothing more or less than restate Bell's theorem, which is that the
Right.
two
It's
diagrams on my PTR don't match. That's what
so
Bell's theorem
so
is.
what you just said is correct. This is the argument in my slide presentation today was an argument intended to bring a concrete example of what Bell was talking about in his theorem. Now your only your only option at this point, and you have two options. I know you follow
Always
both
two
of them,
options.
and those options are, oh, you can believe those options, right? One option is quantum mechanics is wrong. That's one option. You can believe that. Another option is all of the experimenters that have done this experiment, including the pimply-faced teenagers who now do it hundreds of times a year in undergraduate physics laboratories all over the world, are lying to you or trying to impress their professors or in some other way presenting you data that does not reflect what they actually saw when they did the experiment.
Oh, just to be clear, they could have actually seen what they got in the experiment.
Right.
Half of the people who flip coins will get more heads. Half of them will get less heads. All in all, there will be a roughly equal number of heads and tails. But any subset of experiment is going to get more heads than tails. If you create a bounty for people who get more heads than tails, everybody who gets more heads than tails will show up and collect the bounty, and you'll say, look, you can spin
Okay,
random stuff and get more tails than heads.
That's
Every day
good.
of the
So
week,
let's just be
every high
clear.
schooler
Let's
could do
just be
this.
clear that what this is a version of one of the things I just said. This is the version where people are lying to us willfully or otherwise in order to get a reward. And you are entitled to believe that. But let's be clear that there are two
No, you're
options.
confused.
Quantum
You're
mechanics
confused
is
about
wrong. Quantum mechanics is wrong, or all of the people that do this experiment are in one way or another not telling you the truth. Those are the only options. And what you just said was option 2. That was option 2.
Well, technically, nobody has to misrepresent anything in this case. They just have to be more inspired to report when there's more
That's
tails than
option
heads.
2. Come on, Benjamin. That's option 2.
Well, they can. Well, whatever. That's fine.
So John, what
Anyway,
I'm going to do briefly is I'm going to start another room, if that's all right with you, in the club for anybody who's listening who wants the aha of this paper. I suspect out of all the people in the audience who've listened, I don't know what fraction of them. Maybe they could just give a thumbs up or down as to whether they got the aha of this paper, whether it gave you the, oh, that's cool, I get that. The effect that this has on our understanding about local variables. So if you didn't get it, just let me know, because I think what we should do is make sure those people, before they get bored of this argument, have the chance to ask the questions they need to get the aha moment. Because I suspect
I like that
people
idea,
get lost
Ben.
in
You
the
could
details.
start that room, run it synchronously for a while, and I will join, and probably Benjamin will at some point too. But
Cool. I'll do that for people now.
yeah, thank you. I appreciate that. But Benjamin, I do think, I mean, it's really important to understand your options are only those two. Quantum mechanics is wrong. People are one way or the other not telling you the truth. Those are the options.
Well, Einstein's position was that quantum mechanics is wrong. Danny Deutsch's position.
No, it wasn't. That was
Uh,
not it was not his position.
well, you mean because he said it was incomplete and didn't say
Yes.
it was wrong?
Right.
Okay. Well, Roger Penrose says that Einstein said effectively it is wrong because incomplete means wrong. That's Roger Penrose speaking, not me. Roger Penrose has now said quantum mechanics is wrong.
Okay, well, let's be clear, because there's a lot of room for disingenuity here. What Roger Penrose does indeed say that incomplete is wrong, and I think that's right in some sense. But I just want to be clear that Einstein thought that quantum mechanics was incomplete, meaning that he took the fact that quantum mechanics couldn't tell us which light would light. And he said, well, there has to be a way to know because he believed in local reality. He believed that one has to be able to know which light will light because the particle obviously has the property that will determine that. Quantum mechanics just doesn't tell us what it is. And that was a very compelling argument until John Bell showed that no, the predictions of quantum mechanics are strictly incompatible with the local reality on which Einstein based his arguments. Once you know that, Einstein himself has only two choices, because he wouldn't have taken the choice, all the experimenters are lying to us. He had only his only options were quantum mechanics is wrong or I was wrong about local reality.
Yeah, so I think that Einstein's position is not necessarily one strictly of belief. Einstein formulated relativity, made predictions in relativity, and those predictions were demonstrated by observation. That's not perfect knowledge, but it's also not merely belief. So when you get to that point, he is arguing that because quantum mechanics doesn't explain relativity, and in short, it violates relativity.
But that wasn't his argument.
His objection to quantum mechanics was that it violates relativity. Well, come on, that was.
Well, so that's an element of it, but ultimately the important point was that he never thought that quantum mechanics was wrong. He just thought that there had to be a way there had to be more information. Whether he even at the very end of the Einstein-Podolsky-Rosen paper, he said he thought that we could have a better theory, but he knew that he wasn't sure. He thought we could have a theory that would tell us more than quantum mechanics. Even he didn't say that we have to have that theory. He was making a philosophical argument that there had to be local reality, and therefore which light was going to light had to be knowable in principle, even if we couldn't have a theory that would tell us that. When Bell showed that the predictions quantum mechanics make rule out local reality, then Einstein had only two choices. Quantum mechanics is wrong, or I was wrong about local reality.
Yeah, but look, I think the question still remains. I think that when these experiments are done, half of the time they fail. They very often don't report out when they fail, which is weird. It's kind of unfortunate, but I think also it's just.
So this is your option too, right? This is your option too. They are lying to us.
No, I would say that
Yes, one
the
way or the
publishing
other,
motivations,
they're not telling us the
they're
truth.
misinformed. Yes, exactly.
Yeah,
Exactly.
yeah.
One way or another, they're not
And that's
telling us the
fine. As
truth.
I
But
say,
that is a different thing
you are free
than
to
what you
think
said
that. I just
before.
want everybody in the audience to understand that your only options are A, quantum mechanics is wrong, which you have often said, or B, they are one way or the other not telling us the truth, which you have also even more often said. Every argument I've ever heard from you has been a version of one of those two things. And you're free to believe both of those things. I just want everybody to
I
understand
think I
those
believe both
are
of
the
those things. I
options.
think quantum mechanics is, as Einstein said, incomplete, and as Roger Penrose says, is wrong. And I think that the experiments that we're doing right now are not getting at the truth. And I'm thinking there's a pathway here, which is we ignore John Bell and we go back to a different approach, which is not entanglement. We just take a single photon through two polarizers, we spin them so much so that the polarizers rotate 45 degrees during the time of flight, and we see what we get. Now, if we get the results that reflect the state of the polarizers at the moment of observation, then we don't have a local and
Okay.
real world.
You're talking to nobody here, Benjamin. Even I don't really understand the experimental setup you're talking about. But the point is, it doesn't matter, because this is another instance of you doing what you do so often. You take a mathematical proof and you say, but what if we do this experiment and we find out it isn't actually like that? We John Bell
Look,
proved
the
that you
problem was,
can't have quantum
let's
mechanics
agree,
and local reality.
let's
That's a
agree that
proof.
John
And
Bell and Merman's paper,
no experiment is going to overturn a mathematical proof. You then
right,
have, in mathematics, you can prove things. And it's, as I say, that's
I'm
fine.
not
If
suggesting,
you think that we should do another experiment and we'll find something else, you may be right. You should do that experiment. And if you do, and people agree that you do get something else, then we will all know that quantum mechanics is wrong. And I guarantee you that you will get the Nobel Prize for doing that. I guarantee you'll get it quickly if you can prove, as you are, whatever you're saying now is you proving that quantum mechanics is wrong.
yeah, by the way, there's nothing wrong with John Bell's theorem mathematically. It's just that it reduces to two options. It doesn't produce predictions unless you think that um, a two option prediction is a thing. And I just don't think that saying it's going to be one or the other is really a useful prediction. And for that reason, I think John Bell's
I can't
theorem is not
imagine
good
anybody
foundation.
understanding the meat of the argument that you just said. You're not being specific. Let's be specific. John Bell proved that quantum mechanics makes predictions that are incompatible with the concept of local reality. So if you want to show that that you can get experimental results that conflict with that, or that you, or if you, and more importantly, if you can make a theory, if you can construct, I know this is not your specialty, if you could construct a theory that would explain explain the results using the concept of local reality, you would then have, of course, found what you would have shown. Well, no. I have to take this back. The results we get are incompatible with local reality. So that's a problem. What you would have to do is show that the experimental results, which are predicted by quantum mechanics, which are incompatible with local reality, are wrong. That's what you'd have to do in that. And then it would be nice to show to somehow now I'm getting bollocksed up in my brain. You have experimental results which confirm the predictions of quantum mechanics and which are, as my slide presentation here today showed, incompatible with local reality.
There's no chain of evidence.
Yeah, that's right. I guess I'm realizing now that your thesis, if you say that quantum mechanics is wrong, you have to also believe that everybody, you can't, it's not, you have two options. You in fact have to do both things. Your thesis requires you both to believe that quantum mechanics is wrong and that everybody that's doing the experiment is one way or the other not telling you the truth. That's actually, you have to do both of those things.
I think they're definitely not telling the truth.
Yeah.
Look, there we have very little data, but the data we do have, all we would have to do to get classical results out of it is change the arbitrary filters, the farking. We change the farking and we get the
Yeah. See, this is the part, and I don't mean to cut you off, only that nobody here is going to understand your thesis. This is why you need to write it up as a paper and publish it. And it's going to have to be very compelling. And the first people you should run it by are all the people who have done this experiment, especially all the people who've gotten the Nobel Prize for doing the experiment, and see what they have to say about it.
That's like asking Lance Armstrong what the rules should be for the Tour de France.
Well, the problem is that you are and you're a good experimentalist. I mean, I know that as well, but you suffer from this funny thing that often happens to people like you, that the theory means nothing. It doesn't matter what theory says. You think that somehow, you could, or it doesn't matter what you can prove within something else. You think that you might still get an experimental result that shows that something that's been proven mathematically is wrong. Well, so once again, this is what it comes down to. Quantum mechanics makes a prediction. That prediction is incompatible with local reality, and it's what we get in experiments. So your only option is to believe that.
No objection to this Merman paper. I don't know why you're pretending that I do. What do you think my objection to Bell's theorem is, or to the Merman paper is?
Well, I don't know. I'm not sure what your objection to Bell's paper is.
You're getting it wrong. So I thought.
Well, tell me.
You don't understand.
So tell me again. You mentioned a 2 in Bell's paper. I was looking for that. I didn't see it anywhere.
Okay. Well, that's because it's not in there.
Okay.
You don't get the 2 until you format Bell's theorem under CHSH.
I know.
Inequality. Now that's a formalism that allows for experimentation. And
so now you have to prove that you understand what the role that the 2 there is doing. And it's not enough just to say that it's either less than or greater than 2. It's not that simple.
If you look at my PTR, 2, for all intents and purposes, is the straight line. It's the classical result. It's the best correlation you can get across that line. And if you look at the cosine, the sinusoidal, the dotted line, that's the line that's predicted by quantum mechanics.
Yeah.
And that has a limit which is 2 times the root of 2.
Well, so I don't know what you mean by that. Here's what we get from your curve. Your curve shows correlations as a function of angle. Just for clear, the predictions of quantum mechanics are in some sense, and I understand that sense better than I even want to try to explain here, are represented by the dashed line. The predictions of a locally real model, Einstein, if you want, are predicted by the straight line. And the biggest difference between those two happen at 22.5 degrees. degrees. So if you go off to positive 22.5 or negative 22.5 and go straight up, you'll see that the dashed line is further above the straight line at 22.5 degrees than it is at any other angle. And so whatever that angle means, most of the experiments that do these quantum entanglements thing operate with that angle, whatever it means, at 22.5 degrees. And then they ask, is my result closer to the dashed line or is it closer to the straight line? Now, if you take a single measurement, you're not going to know. But at some point, you get, let's say the difference between those two, just to take a number. Let's suppose the difference between the dashed line and the vertical line and the straight line at 22.5 degrees. Let's suppose it's 0.1, right? If you get data that shows that the actual result is the dashed line, is right on the dashed line, plus or minus 0.01, then your data is saying it's definitely not the straight line. If you get data that centers on the dashed line with an uncertainty of plus or minus 0.1, it could be the straight line. If the uncertainty is as big as the difference between those two, then you haven't really had anything to say. It's when the uncertainty in the experiment is much smaller than the difference between the dashed line and the straight line that you start to be able to say something. And that's what the experiments say. When you do the experiment, you get the dashed line plus or minus an amount that is much smaller than the difference between the dashed line and the straight line.
And how much poetic license do you think is used here? Like the kind of poetic license that the oil drop experiment. What's the guy's name? Merman? No, not Merman.
So this is option 2 again. They're lying to you.
Who is the oil drop
Millikan.
guy?
Yeah, Millikan.
Millikan. How much Millikaning you need to get from one to the other here?
You're flailing, Benjamin. It's fine. You can believe that people are lying to you, but I'm just telling you that the experiments that got the Nobel Prize effectively, if you want to reduce them to your diagram, what they got was a data point at 22.5 degrees, which was on the dashed line with an uncertainty that was much smaller than the difference between the dashed line and the straight line.
Well, we can't possibly know that because we don't have access to independently analyze the data.
Okay, that's option 2 again, right?
Yes, it's option
right.
2.
That's fine, but I'm just saying that's how science is all. That's how we found. That's how we found the Higgs boson. It's the same thing. If you want to make a strong statement, you have to have an uncertainty. When
there's chain of evidence for the Higgs. There's no chain of evidence for quantum.
Yeah, I know. I get it. I understand. I'm just telling you how science works, and you're free to believe that scientists are in a massive conspiracy to lie to you about quantum entanglement. That is a thing you are free to believe. But this is how science works. When in the 19th century, when almost 200 years ago, people started noticing this tiny little difference between the precession of Mercury's orbit over time with the predictions of Newtonian theory. Newtonian theory predicted that it should precess, and it predicted it correctly with a discrepancy of. It predicted that the major axis of Mercury's ellipse should rotate in inertial space at an angle. I don't remember what the prediction was, but the prediction from Newtonian mechanics was different from the observation by less than a 60th of a degree, less than a 60th of a degree per century. We had a very, very tight observational value for that precession and a very tight theoretical prediction from Newtonian mechanics, and they differed by less than a 60th of 1 degree per century. And that caused a major crisis in physics because that less than 1/60th of a degree per century was much larger than the uncertainty in the observations and the uncertainty in the theoretical calculations. If either the observations or the calculations had had an uncertainty of 1/60th of a degree per century, there would have been nothing to get our panties in a wad about. But it was the fact that there was a difference that was much bigger than the uncertainty that caused the turmoil. And it's the same thing here. When people do this experiment, they get the dashed line with an uncertainty that's much less than the difference between the dashed line and the straight line.
But if they don't show the raw data and
Okay,
allow
that's right.
third
They're
parties
lying to us. I
analyze
get
it,
that.
then they can get whatever they want. Now,
That's fine.
here's the problem. Just like Lance Armstrong, science is a competition. People are vying for the gold trophy there. Usually it's the Nobel Prize. There are other things, Fields Medal, etc. It's and every day it's a rat race for a grant and a chair at a university and so forth and so forth. And because it's a competition, it has the same qualities as the Tour de France. And it's no surprise to me that when you look at the people winning at the front of the pack at the Tour de France, all of them, and I mean every last one of them, is shooting up something into their bloodstream to make them go faster.
Okay.
Because as
So
soon as one of them is allowed to win that way, the other ones have what you call a choice, right? They can either lose or they can cheat. Those
so
are the two
here's
options
the
that you have in a
difference.
competition where at least one person is like Lance Armstrong is cheating. You can
Here,
lose
here's
or
the
you can
difference
cheat.
between the way science works and the story you just told. In the case
Okay.
of bicyclists shooting up, doping themselves, there's no way for anybody to win other than to dope themselves. Of course, short of something that prevents people from doping up. There's no way for that to happen. The difference
Well, they could be a
here,
genetic freak,
the,
right? They could
difference
modify
here
their genes or something.
the difference here is that somebody could do an experiment and show that, in fact, all of those people who have done the experiment before and gotten the Nobel Prize for it were wrong. They were, in one form or another, not telling us the truth. You could do that, and you would get the Nobel Prize for doing it. So there is just an enormous incentive to show that all of those people are wrong. There couldn't be a stronger incentive because once again, as I say, if you can show that all of those experimental results that have been reported were wrong, one way or the other, that here's what they did wrong, here's what you actually get when you do those experiments, or here's what you actually get in conflict with quantum mechanics when you do some other experiment, you would be showing not only that they were wrong, but that quantum mechanics is wrong. And I guarantee you that you will get the Nobel Prize for doing that. There can be no greater motivation for scientists to try to do that than the fact that they would get the Nobel Prize if they did. There's nothing in it for a scientist to get the same result that the Nobel Prize has already been awarded for.
That's like saying that you would get a gold medal for winning the Tour de France if you could just prove that Lance Armstrong was taking drugs. You could prove that Lance Armstrong was taking drugs, they wouldn't give you the prize.
No, but it's subtly different because in the case of science, you would be showing that quantum mechanics is wrong.
Well, you have that belief, but I don't think that that's true because the evidence is an article by John Clauser himself in Caltech, which describes Harvard doing this experiment and getting.
Oh, Benjamin, please. I'm going to have to end this room because I'm going to lose my shit if you really go there again. This is a story for everybody who doesn't know that at the time John Clauser did his experiment that everybody told him not to do because everybody knows what the result's going to be. Some other people in Harvard did the experiment and got the result that Clauser almost certainly wanted to get himself. And he was in communication with them, and they ultimately did not publish. Now, Benjamin's version of this story is that one way or the other, they were suppressed. That was not what happened. I just guarantee you that's not. You, everybody's free to come to their own conclusion, but the reason they didn't publish was because Clauser convinced them that they had made a mistake. And I don't know the details, but anybody can look into this. It's well documented. The reason they didn't publish was not because somebody threatened them, because somehow they thought, oh, this will be bad for our reputations if we tell the truth. Nothing could have been further from the truth then. They got the result Clauser almost surely wanted to get because he knew if he did, he would get the Nobel Prize. But he managed to convince them that they were wrong. You think they would have not published because John Clauser, who's just this nobody from Berkeley, says, oh, you better not publish that. Somehow he wielded some power to make them not publish their result. That's just nonsense.
John, can we?
Yeah.
Can I go back to just like
Steve, go ahead.
real questions about this?
Yeah. Oh, I don't know if you were here. Ben Tristram has opened another room on the paper, and we're all going to go over there. Go ahead.
Well, here's the deal. I don't want to throw shade on Ben, but the reason I came here is because he said something which I think is totally wrong, and I so I thought the whole point of the experiment, right? He was talking about it in terms of, well, there's nothing in the particle that determines the color of the light. I mean, that's not true, right? What's true is that it's not fixed, and you don't know what the property is going to be that's going to cause a certain color of light until there's a measurement of either of the entangled particles, right? It's not that, I mean, he almost made it sound like there's nothing in, right? It's not that there's no encoding in the particles. It's that you can't know what it is until it's measured. And if it's entangled with another particle, measuring one affects the other. But they collapse into some sort of fixed state when they're measured, right? Isn't that an accurate way to describe it?
Yeah, I do think, I mean, it's important to understand that in this idealized experiment that I described, the light that flashes is effectively the measurement of the property that's causing it to flash.
Right.
Yeah.
So that property, right, you can't say that it's fixed from the moment the particle is created and it never changes because of these concepts I don't understand between superposition and collapsing into some fixed state. But that's what happens, right? It's that it's indeterminate. It's not that
So that's what
is no property.
Yeah, I want to be
It's indeterminate until it's measured.
Well, let me just say, I think that's
it's really good. But can I just reserve one question for Steve on his expertise?
Benjamin, with all due respect, I would rather just that John answers.
let me just answer it, and I think you'll be.
I wanted to ask you a question. I didn't want to.
Well,
answer.
I would rather stay with John's room, and I can't answer questions about physics. So let's let John answer my question.
Yes. So hold on. I think you'll be satisfied with my answer, Benjamin. I mean, you said it a little more certainly than I would. I would say that the light that flashes is the measurement of the property, but that alone doesn't mean that it wasn't known all along, right? I mean, the point is that what we learn from the analysis of this data is simply that it can't have been the case that that property was known before, just from the statistics, right? That in other words, the 1/4 thing is incompatible with that. And that's a prediction of quantum mechanics. There's nothing, I mean, any normal person would think, well, that property had to have been fixed. Einstein certainly did. And he compelled a lot of people to think the same thing. The point of Bell's theorem, which came unfortunately after Einstein died, was to show that Einstein's just core belief that there had to be local reality. Not that it's wrong, but that if quantum mechanics is right, then it's wrong, right? That quantum mechanics is incompatible with that thesis. And so you can't have local reality and quantum mechanics. If you want local reality, you have to show, or you have to believe that quantum mechanics is wrong, and then the nice thing to do would be to show that it's wrong by showing that it makes predictions that are not what are observed.
And can I ask one more follow-up to my very first question?
Sure.
And again, I know I'm way out of my depth with all these questions, but not full. Like I hear, like as a general statement, that like sort of quantum states don't really have much of an impact at the macro level because they get swamped by other effects. But is this reality used in ways like, it just seems to me when two particles at great distance, and I know focusing on the distance aspect isn't the whole story, can sort of affect each other in this way, if that's even the right word to use, that it just seems like it would have really fascinating scientific applications. Do those exist?
Yeah.
And if they don't, is it because we can't control, we can only measure, or is it because
That's such a good
affecting
question.
these quantum states doesn't really have macro effects? Like, I know that's a very big question, but
No,
I'm just trying to get a handle on it.
No. Once again, it's really good in several ways, and it is, of course, the thing that Einstein was concerned with, and Benjamin is as well. So I'll just say, first of all, it is the amazing thing, of course, comes this whole entanglement thing isn't spooky until it starts happening at distances that are so large that there can be no communication between the measurements, right? That's when it gets spooky, and it is spooky. Doesn't makes it no less a prediction of quantum mechanics, but it is spooky, and that's the loophole. Clauser's experiment didn't rule out communication between the detectors, although it's weird to think that there might have been, because it would imply that nature itself somehow conspires, to communicate behind the scenes, which would be a weird thing. But because you have to, you can't just say it doesn't happen. People have gone to greater and greater and greater lengths, ending with Zeilinger back in, 10 years ago or something, so he had two detectors that were far apart. I don't know how far apart, but they were then the essentially the selection of the switch setting, if you want, was made randomly using light from a quasar that was 10 billion light years away in one direction. Yeah. And that's the length that they've gone. So that's the length that they've gone to make sure that there's no communication, no kind of subtle coordination between the detectors. Now, Sabine Hassenfelder has a theory called superdeterminism, in which that light from those quasars is correlated because of this super deterministic thing. Even though they haven't communicated maybe with each other for billions of years, they were set into the states they are. They produced the light they did. The light that's picked up is used in the way it was always predetermined to be used to set those detector settings. And it's a kind of an extreme form of nature actually conspiring to give results that look quantum mechanical, even though nature isn't quantum mechanical.
And even though I know it's a massive subject, can you say anything about some of the practical scientific, like, are there ways in which people are harnessing this quantum reality to create tools that do things?
Right. So quantum entanglement is at the heart of quantum computing. Quantum computing relies on quantum entanglement. But the thing you'd really like to do is use this apparent faster than light thing, whatever that is.
Right.
You're right. And that's the thing you'd like to use. And if you could do that, then you would show that relativity is wrong. If you could actually make use of that to send a signal faster than light, send a message, right? A content bearing message from one place to another faster than the speed of light, you would be showing that relativity is wrong, because relativity rules that out. If that can happen, then you can travel back in time effectively. You can send messages to somebody to kill your grandfather before he had your father, things like that. You can do all of these things that we really can't allow to be able to happen. Oh, sorry. Okay. Okay, good. Let's go over there. Let's go over there. Benjamin, I'm sorry. I think my final thing to you, and I think you would agree, is that, you have some combination of they're not telling us the whole truth,
Yeah, I was
and
just
quantum
going to
mechanics
ask
is wrong.
Lee if there was room for it, but I know censorship is a priority here.
Oh, well,
The
he just left. So,
yeah, well, I was going to ask him what to make of the fact that there's no chain of evidence on these
yeah.
experiments.
Yeah, okay. Well, maybe another
But let's
time.
make sure we don't answer that question, because we don't really want to know the answer, right?
Yeah, that's right. Because because once again, I'm a part of the great conspiracy that is lying to
Because
you.
it's too upsetting. If Lance
No,
Armstrong is not the winner, then America's not the best country, and we don't get to rally
well,
around the
it's
flag.
not that.
And there's consequences.
I urge
There's
you to show.
consequences.
As I say, I can't prove to you. I cannot prove to you that quantum mechanics isn't wrong. I cannot prove to you that everybody doing this experiment isn't lying to you. I can't. You are free to believe that. But I just want everybody to understand that that is what is required. In fact, it's more than that. You have to believe both. The only way.
Do you now believe, at least that I've proven over the last 3 years, that all three of the people who got the prize have in some way or another managed to not publish the data?
Yeah, I actually don't know that, but I'm even willing to concede that to you. It
Right,
may
okay.
be true. It may be true.
So you're asking
but
me to trust me, bro?
well,
on-
no,
on their
no,
experiments, but
I'm
we
not.
Don't get to
I
independently analyze
I'm
the
not
data.
at all. I'm not at all. I'm telling you, please, please do whatever you like. You are free to, as I now realize, both. You have to do both. You have to believe both that quantum mechanics is wrong,
As Einstein and Roger Penrose
right,
do.
the quantum mechanics is wrong, and that all of the people that have done this experiment are one way or the other not telling you the truth, and you're free
What
to
do you
believe
think-
that.
What do you think Roger Penrose thinks of the same people if he's
No,
saying quantum mechanics is wrong?
Now there you're just being dishonest, because this is miscasting what Roger Penrose thinks about quantum mechanics.
Not that much.
It's not about no.
Not
It is
much.
completely. This is my last word, Benjamin. This. Yeah, well, and this is my final word. Roger Penrose doesn't take issue with the results of the experiment because he doesn't think quantum mechanics is wrong. He thinks
Roger
that
Penrose has said quantum mechanics is wrong.
I know.
Well,
I
didn't say
understand that
because
he
doesn't
has
believe it.
said that, and
So now
you.
he
This
believes
is
things
the.
that are completely
Oh, Benjamin.
because
Oh God, you're
Roger Penrose
just
has a problem. He doesn't know how to express himself.
you're doing it again. You really are doing it again, Benjamin. The thing with Roger Penrose is he thinks, like Einstein did, that quantum mechanics is incomplete. He thinks so in a different way. He takes no issue with entanglement experiments. No issue. He does not think anybody's lying to us. He thinks quantum mechanics makes the right predictions, but he also thinks that quantum mechanics needs a better way of understanding measurement, understanding the collapse of the wave function. That is not your position. Your position is that the predictions of quantum mechanics are wrong and that people are lying to you. That's your position. And with that, I'm going to end this bite of physics.
See you
Okay,
soon.
and let's go over to the other side. I'm just going to end it today. Here we go. Bye bye.